Okay, so in this video, we're going to be looking at significant figures and scientific notation because the two ideas are actually quite interlinked. So how high is Mount Everest? This is a good example of why significant figures are important. So in 1856, this guy, Andrew Waugh, he declared that Peak 15, as he knew it then, was exactly 29,000 feet tall, 29,000 feet. And like all great people, he decided to name it after someone. He named it after his boss, Mr. George Everest. That's right, not Everest, Everest. So this became, Peak 15 became Mount Everest, named in honor of Mr. Everest. But the problem was he didn't really like this number. It was too round. He spent many years calculating this without a calculator, but he came up with this lovely number. So he actually changed the number and he made it 29,002 feet. Hence the old joke, who was the first person to put 2 feet on Mount Everest? It was this guy, Andrew Waugh. So he had this number, Mr. Waugh, of 29,000, and he wanted to tell people that no, he definitely had measured all of those zeros we can see at the end there. So how do you tell people you measured 29,000 to the nearest one when people are looking at it thinking, well, maybe you measured to the nearest 10, or maybe you measured it to the nearest 100, or maybe you measured it to the nearest 1,000. How can we tell the difference between those numbers? And we can see it because we got this multiplier here. Let's expand that idea a bit more. We could say, we're going to do it one more step, which is 2.9 times 10,000. Okay, now if you look here, we also know that we get tired of writing all those zeros. So we're going to write 10,000 like that. We're going to write it in index notation, and then the number becomes a lot more easier to handle. So what we're looking at here, if we ever look at any of these numbers in scientific notation, so in scientific notation, you have your number, which we're going to call, this part is going to be called the coefficient. And it's multiplied by how big the number is. So we're going to call that part the magnitude. And that just means how big something is, how magnificent something is. Okay. Now, if you look at this number here, when we've done it as 2.9, we can see there is two numbers here. Okay. So that has two significant figures. So we can tell how big the number is. It's in the 10,000s. And we can look at it and say it has two significant figures. But what Mr. Waugh wanted to say was, no, it's not 2.9, it's 2.9000. He said all of those zeros have been measured times 10 to the 4. It's still the same number. It's going to be the same size. So it's the same magnitude. But the coefficient has changed. If we look at this one has a whopping 1, 2, 3, 4, 5. This has 5 sig figs. I wouldn't call them sig figs because that's a lot of people do. And we can see that now it's very clear when I'm using scientific notation how accurate my measurement is. And you don't have to cheat and put 2 feet on the end of your number to make it look good. Now in science, lots of big numbers turn up. So if you do any chemistry, you might have seen this before. This is Avogadro's constant. As you can see, it's a very big number. And there's all these zeros. Look at that. You've got all of those zeros. And so you have to sit there and count them all and stuff. So you can start to understand why people don't write it this way. So we could start with the number part. And the number always must be 6, and we always put the decimal point right there. I'm going to go 0 to 2. Okay, so this first number is the only number on that side of the decimal point. So there can only be 1 to 9 in that place, okay? And so any other numbers have to be put after the decimal point. And when we got to work out how many places we're moving this decimal point. So actually the decimal point is starting here. So we have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So this number is 6.022 times 10 to the 23. And don't forget our unit, that's per mole. So you can see it's much easier if you actually write a number like this, because all of those zeros under that green line, all of that, they're just placeholders. They're just telling us where to put this part of the number, okay? And so we can see quite clearly this has been measured to how many significant figures? So let's count them. We've got 1, 2, 3, 4. So that's 4 sig figs. And the rest of those zeros, we don't need to write them down every time, or you can see it's quite a pain to actually count them. So we just ignore all that and we just put it down here as 10 to the 23. And that's much easier to handle that number. So we looked at a really big number, Avogadro's constant, before. Here's a really small number. Now, this is obviously our important sig fig part. So we got 4 sig figs there. And all the rest of this part, all these zeros, they're not doing anything. They weren't measured or anything. They were just there to tell us where does the 9 start. If we had it in a different way, it'd be a different number, a different magnitude. So we have to count how many times we moved it. Now this one's going smaller. Now technically it's the number that's moving, not the decimal place, but when you're written it down, you've already written your dot in, it's easy to do it the other way. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So in scientific notation, our mass of electrons should be 9.109. That's accurately measured to 4 significant figures times 10, and we went backwards. It's getting a small number, so we put a negative 31, and of course we put a little k and a little g for kilograms. Wow, as you can see, it's really, when you're looking at these big numbers, and you often do in science, you really don't want to be looking at all those zeros and having to count them every time. And if we look at this, we can compare the size of things quite easily without having to look at all the zeros. So if we were to look at these things, the only part we have to look at is the magnitude part. Now, quite clearly, although we can see 9.109, and you might think, oh, 1.672, well, which is the bigger one? It's the 9. No, it's not. There's a difference of 4 here between the minus 31 and the minus 27. So that's minus 31, that's minus 27. That means 4 decimal places moved. So actually, the mass of a proton, we could say it's approximately 10 to the 4 times more massive. What should I say? Not heavier, more massive. Okay, so the proton is 10 to the 4. It's 10,000 times more massive than an electron, roughly. We can just look at the order of magnitude for these things. So it's the order of magnitude, remember, tells us about the size, and the coefficient part tells us about the number of significant figures. Both of those measured to the same accuracy. Okay, let's look at some more examples. Here's a big number. And let's have a look what that means. Now, here's a kind of a rule you need to understand. So this 0 and this 0, they're between other numbers, so between numbers. But these two dudes at the end here, they're not between the numbers, so we would call those guys placeholders. So they're placeholders. So when I look at this number and how many significant figures does it have, we can see this is the boundaries of our sig figs. So that's the sig figs part. So the placeholders aren't included in the significant figures. So this number has 6 significant figures. So that's got 6 sig figs. Okay, and so if we were to put that into our scientific notation, which we're getting the hang of now, we would write it as 3.04016. And then we're going to multiply that by a coefficient. Now, to get back there, we've got to go a few moves. Let's do that in another color. So we've got to go 1, 2, 3, 4, 5, 6, 7 moves. So that means we have got to be saying times 10 to the 7. And that'll put the 3 back in there. And we can see our significant figures are quite clear there. Those 2 zeros, we assume, unless we're told otherwise, that those 2 zeros are placeholders and they're not significant figures. But the 0 between the 3 and the 4 and the 0 between the 4 and the 1, they are between numbers. They are part of the significant figure. Let's have a look at another one, which is let's try a small one. So we've got 0.00180930. So which ones are important? Well, that one, so between numbers, and these are definitely placeholders here. That's just moving the 1 and the 8 across, and also this one. So we got our placeholders here. That's a placeholder. Those are placeholders. Now, unless someone tells us that last 0 was measured, it is considered a placeholder. So we then look at our number. We write 1 digit. Remember, we only have 1 digit, and then the rest have to be after the decimal. 8093. And how many moves do we make to get there? Well, 1, 2, 3. So we've got to go times 10 to the negative 3. Remember, negative because we're going the other way. We're making it a smaller number. So this one, we would say has, well, let's have a look at that. That one's got 1, 2, 3, 4, 5 significant figures. So that's 5 sig figs for that number. And so we're starting to get the hang of here of what counts as a significant figure and what placeholders are and how to write up this notation.